Alex Matrosov. Modern secure boot attacks. Many hardware vendors are unmooring modern security boot by moving root of trust of the hardware. In this presentation, I'll explain new security issues to bypass a specific implementation of Intel bootware technology in one of the most common enterprise vendors.
Hello, Ekoparty, and I'm glad to be on this stage second time on this conference. And my talk it's about attacking hardware root of trust in common implementation in UEFI Firmware. So just a reminder, I'm Alex Matrosov. I'm working for NVIDIA, leading offensive security research there, and I did a lot of stuff regarding UEFI Firmware security research. So just a small disclaimer, I'm not talking from my employee point of view. I just describing my own research, and all bad jokes and mistakes, it's on me, and of course 0 days too. So for the target of this research, I take a Lenovo P50 laptop, and before I was mostly targeting Gigabyte, Asus Tech, and MSI, so no more baby targets. I took a serious enterprise laptop to basically prove it has a lot of issues too. So in this talk, we will be talking about what is a hardware root of trust is, and also we will be touch some architectural mistakes. Not architectural mistake, but let's see, in reference implementation, Intel provide a lot of freedom to OEMs who basically make mistakes in their implementations. Also, we will talk about the compute trace and implementation of compute trace in Lenovo laptops, nowadays laptops. And interesting thing I found recently, over Windows management interface, you can actually call SMI handlers. And probably, as you remember from my previous talk yesterday, SMI handlers, it's kind of like a callback function from the operating system level directly to the BIOS. And sometimes it's directly call the code inside in the most privileged mode, system management mode on x86 systems. So let's start about what is a hardware root of trust and what is the problems actually implementation of hardware root of trust. In most of the cases, hardware root of trust should be implemented in RTL, that means directly in the hardware and silicon, but silicon, RTL level, it's hard to modify. Actually, it's no way how you can modify it after releasing the product. And of course, it's create a lot of limitation for the companies to implement their root of trust that way, because if something happens, they can patch it. And because of that, hardware root of trust is a kind of mix between the firmware level and the hardware. Also, common marketing tool, even if one bit inside the hardware locks something, the vendors say it's a hardware implemented root of trust or hardware implemented technology for protecting something. But it's not exactly true, because one bit it's not really a security feature, it's just lock mechanism, which is in reality have many ways how it can be bypassed. I will be back on this slide, and actually probably you remember from my previous presentation yesterday, it's because, as example, BootGuard as a technology for the measured boot has a root of trust based on TPM. And TPM already have a proven research from Jeremy Boone and Trammell Hudson, how they basically can attack the TPM or attack the TPM communication between the actual firmware, BIOS, and the TPM, and fake the responses from TPM to the BIOS. It's a boot flow for the BootGuard, and let's see how it should be work in the perfect world. We have a CPU reset, and the microcode make attestation for BootGuard Authenticated Code Module, and Authenticated Code Module make attestation even before the reset vector for IBB hash, which is kind of like hash for first stage of the bootguard technology, and it's make attestation for transition from the ACM to the starting loading the BIOS on the actual boot process. So, looks perfect, all the transitions secure, and what it can be wrong, right? So, first of all, bootguard doesn't cover the microcode and ACM. So basically, if we have any vulnerable versions of ACM and microcode, we can downgrade them. And we can basically use one-day issues to attack this technology. So if bootguard ACM is compromised, and if we downgrade the microcode with known issues, it doesn't make sense on all the checks which exist on upper level boot process inside the BIOS firmware, because it's already done, it's compromised, right? So it's how the reality are. But why we don't lock everything inside the hardware and let the firmware just boot it trusted? So first of all, OEMs don't like lock secrets because of supply chain hell support process. The cost of the vulnerabilities is very high, and I mean cost for the vendor, because you can't release patch for the hardware, and basically you need to recall your hardware to replace it. As example, Google recently make a recall for their dongles with a Titan chip first version, and probably it's cost a lot of money for them. So the cost for the updates is really high, and all the vendors try to basically reduce the secrets which is locked inside the hardware because of that, because the price for these issues, for basically fixing them, it's very high. And in the most of the cases, we can see the mix of the hardware and firmware, and it's how the reality looks like. But let's talk about connection of operating system level, firmware, and some of the hardware related secrets. So probably you remember from my talk, or you know what is a system management interface, SMIs. So, and it is a PowerShell script which is basically get some information from ACPI table about what version of the laptop, what version of the BIOS, and etc. It's basically the information enough for the attacker to create payload for specific version of the laptop, and you can get this automatically. Also, the same way with the PowerShell can disable the boot guard in enterprise laptops. But I will not talk much about that because I covered yesterday. Let's go to Windows Management Interface directly. And this picture actually I steal from Lenovo official documentation. You can see the links here. And you basically can look. So basically we have this Windows Management Interface from Lenovo, which is basically communicating directly with the BIOS settings. And as the researchers, we will think what we can basically change from that, right? And actually we can change a lot. But most interesting ones, I would say it is this ones. Oh. So it is this ones because we can enable, disable secure boot. We can enable, disable TXT. We can enable, disable virtualization, and even VTD for protection of DMA attacks, direct memory access. So think about, basically, if we have privileged access to the laptop, we can do whatever we want, even from operating system level. We don't need actual physical access or BIOS exploit because we have everything in Windows Management Interface. So, and also, of course, you can find all these structures for basically modifying it in ACPI. Directly, if you go to DSDT table, ACPI table, you can find everything related to this management interface. And it's a sample script which is basically change password for the BIOS administration from the operating system level. Scary, right? So, and it's actually how this research gets started, because I was thinking, okay, what I can do more from this system management, Windows management interface, and actually I can do a lot, because Lenovo have a Dixie driver with remote configuration. It's the name of the driver. Interesting. It has a Lenovo setup automation and setup under OS SMM. And it's get me super interested what is inside, especially these ones. So Lenovo setup under OS, Dixie driver mostly communicating with Lenovo password manager settings inside the firmware, and Lenovo under OS, it's basically responsible for BIOS password and BIOS settings. And it has a 12 SMI handlers, which is actually a huge attack surface. Lenovo hidden setting, it's already kind of interesting name, right? For the driver. It has two functions for compute trace enable and disable. And compute trace, for you, if you not remember, it's kind of a rootkit for basically tracking your laptop this technology been developed for anti-theft purposes, but honestly, it's been already in use for the malicious purposes by some of the APT attackers. And setup automation have 4 SMI handlers for configuration, password, and boot order. But boot order actually it's important because it can, as example, change the order of the boot devices. And if you connect physically USB flash drive with something malicious, you can basically put on the first place your drive before the operating system boots. Also, secure boot configuration has a lot of other options I will talk about a bit later on the next slide. And specifically, automation for SMI have 12 other SMI handlers, which is all of this information is undocumented. I basically recover based on reverse engineering, and these ones I not recover yet. It looks well very interesting and promising too. So, but let's back to compute trace. Why compute trace is interesting? First of all, last year ESET been discovered the rootkit LowJax, which is based on this technology to persist inside the system. And in Lenovo BIOS, we do have 6 Dixie drivers, mostly in SMM, which is basically responsible for orchestrate this technology inside your machine. And we have like a compute trace installer, which is basically install operating system component on your system automatically. We do have a compute trace enable, which is basically enable the technology and disable. But I was thinking, okay, if we disable compute trace on your BIOS settings, it will be really disabled, or it will be still persist on your system. And also, Lenovo remote configuration is actually most interesting one. That means maybe you can remotely activate compute trace on your system if it's really not deactivated, right? So back to research in 2017, what I did for recover compute trace SMI handler, it is actually a lot of interesting information I will talk about on the next slide, but what I get from that research, we have this option, current setting, disable permanently compute trace. You can see here, so. And honestly, it's a bullshit option. Compute trace still active on your system, but basically it's not doing something bad, but it's still active. That means the attacker can activate it. You can actually find my slides for previous presentation by this link. So honestly, it's no permanent disable feature for CompuTrace if it exists on your laptop. Let's talk a bit about the architecture of CompuTrace. So we have a Lenovo security config and Lenovo hidden setting, which, as I mentioned, both these configuration storages not communicate, but dependent by Lenovo CompuTrace services. And CompuTrace services actually use Lenovo security semi-dispatcher and Lenovo mailbox for orchestrate activation, deactivation, and activity. So I was looking on Lenovo security config to recover this structure, and some of the fields it's still unknown because I don't know what they related with. But you can see also a lot of things like access to the camera, access to the microphone, CompuTrace, Intel VTD, secure boot, rollback prevention, and many others. Even device guard is there. So it's kind of like very interesting place to look for. And I was thinking, okay, what we can do? It's disassembled CompuTrace services Dixie driver, and actually it's directly tied to modify values in this configuration table. So, and of course, here is some services which is basically orchestrate this activity from operating system level. And the name of this is my handlers, it's CompuTrace enable, disable, and CompuTrace state. That's kind of scary because you can just call one of them to do something with Lenovo security config, right? And CompuTrace SMI services, actually, it's kind of registered callbacks in Windows management interface. That means you can, over Windows management interface, call these objects. So, and you can see basically how this structure present inside the CPI table on your machine, and where the bits is 0, sometimes it just orchestrate, okay, secure boot is on or off, secure boot is, other option off, on, off. So, and user flash update, which is basically allow you from operating system level update your BIOS. And I was thinking, okay, but let's back to permanent disable option, because I want to understand how it works. And basically, after reconstruction, this assembly code, it's just if secure config CompuTrace true, then CompuTrace enable is active. If not, then it's disabled, false. Kind of like funny for permanent disable option, right? Also, for disabling and enabling, you need to communicate with CompuTrace state, which is basically have kind of like specific canary value, but its canary value is hard-coded, and you can see the defines. So back here, it's about CompuTrace state. So we have 4 options, basically. Enable, active, disable, and disable secret key, which is basically deactivate permanently CompuTrace on your machine. And secret key is just 4 bytes. So it's a word value. I was thinking, okay, word value, it's not very easy to brute force. But when I was reverse engineering derivation algorithm for key, I can see it clearly. Here is no 4 bytes. It's actually 1 byte, because other bytes don't have any sense in this decryption algorithm. So then I was looking on this comparison key check function, and it was a constant time. If it is a constant time, it's brute forceable because you basically can understand when the key is different and when key is good. So you can basically brute force fast to get your correct value. So basically it's side channel attack possible on this algorithm. Okay, so we have 1 byte secret key stored in SPI flash in VRAM. We have different laptops, of course. Some of them have a different keys, but I use a chipsec. It's open source framework on GitHub for basically call the SMI handler and just check specific value. So, and in my case, disable value being 57 in hex. Not difficult and also kind of scary for me because this option for permanent disable and also after you use permanent disable for compute trace, it's still active on your system. If we switch our focus a bit further, what else actually we have in our laptops which has additional vulnerability landscape? It's embedded controller. And embedded controller, in many cases, it's not a security boundary for the vendors who develop the hardware. So, but it's quite complex actually nowadays. Microcontroller, and in Black Hat research with Alex Gazette this year, we've been presented how we break this microcontroller. You can find the slides on the Black Hat website. But let's actually talk about other vendors, because we was breaking microcontroller which has an authentication, and we break authentication. But if you look on this updater for a gigabyte laptop, it doesn't have any authentication. You just basically flash directly from operating system level the binary blob on your microcontroller. And like embedded controller have some callbacks to the BIOS. And basically this attack surface is not very known and well documented and never considered as serious problems. So basically what happens, you change your security boundary because architects was thinking, okay, the attacker will come from the operating system level, but what happens, the attacker attack embedded controller and attack from other side of the boundary. That's interesting, different point of view. Okay, Intel boot guard. And let's discuss some ways how we can bypass it. So, how hardware root of trust actually became a software? First of all, recovery mode is evil, and it's hard to implement security in hardware related to recovery mode correctly. Security transition chain of trust on different boot stages is very actually slow, and it's why it's hard to implement securely. Because if you will be verify everything on each stage, your computer will be boots probably minutes, but all the vendors won't blink your screen like in a second. So that means they should optimize verification chain of trust, and especially the transition between different boot stages. In most of the cases, without hard reset of trust moves purely from software for performance purposes. What that means? When you go to the sleep and hibernate, all the transitions not verified from the beginning, basically from the root of trust inside the hardware, it's verifying from the some state which is being safely stored inside the BIOS in software. Enterprise hardware also need a remote update tools. And nobody use Intel BIOS Guard, and mostly all the vendors try to avoid this technology because it makes recovery very hard. So basically, it's flow for flashing BIOS image on the NAC machine. And we can see here flash an image for recovery block firmware image done. And it was me curious about what inside the recovery mode. And if we look on verification result, for this check, it's stored inside the BIOS in software. So what that means, we have a hash, which is kind of like make a transition, the root of trust from hardware to this hash. And if we make a recovery, it will be rely on the hash in software. So hash is like SHA-256, it's not brute forceable. Here is about we can change this hash. Then, when verification happens, it will be verified with our hash. But for that, we need a vulnerability inside SMM. So also, I was thinking, okay, what else? But for recovery, specifically on NAC systems, it was just ignore this cache and make a recovery started. So this vulnerability actually been presented by Alex Yermolov on Zero Nights last year. And he found this vulnerability inside the hop driver, inside the BIOS. So yeah, here is a flow, reconstructed flow, and you can clearly see here is basically starting the recovery process. But what does that mean? We have two sides of the boot guard technology. First side is baked inside the hardware and basically locked by the fuse. And this fuse have a hash value which is try to protect early stages of the boot. But we also have a lot of components relies on the firmware only, K-manifest and initial boot block manifest, all of them present only on the firmware. And if we don't need the hardware part, as in recovery mode spoken before, so we have only the firmware side. And all this can be modified to present correct boot for the malicious components or modified components. So basically, back to this picture, why it happens. Also, one more interesting thing I found is boot guard Lenovo PCD init option. So basically, in Lenovo laptops, some of them, they have a PCD platform configuration value. It's stored inside the BIOS, inside the padding. And when I was reverse engineered Lenovo PCD init driver, I was found this check, and actually this check verify this value. If this value true, then it disables the boot guard, even if it's enabled on your system. And actually it sounds like clearly as a backdoor or maybe a recovery or support mechanism, I don't know. So basically, we can dig inside the system and found a lot of things which sounds differently as the vendors claim. And my opinion actually, this particular check been created probably not in backdoor purposes, because when you have your laptop and you came to support, say, oh, my laptop doesn't boot correctly, what they can do, because if your laptop is locked by hardware root of trust, they can't change anything, even like access to the BIOS, and they create this kind of mechanism. It was hidden, but as we all know, security by obscurity doesn't work, right? So, and of course, it's easy to discover. So, I don't know, somehow this driver get my attention, and then I figure it out. We have this padding, and this padding doesn't protect it by BIOS boot guard. So basically, you can modify it. So also, I want to pay attention on this tool. It's UEFI tool. 2 years ago, I developed mechanism to verify IBB for the boot guard, and these colors, as example, red colors mean something it's not protected fully on the boot guard hash. So, and not colored values, it's just not covered from boot guard at all. So, and you can see this padding highlighted by blue just because I put my cursor there. So, and it's not protected at all. And yeah, you can just modify it, flash bias back, and actually it's not affect integrity because it's not protected by boot guard, right? In many cases, so for usability purposes, enterprise world needs some mechanism for recovery, right? And this, many cases, it's enemy of security. The vendors understand permanent disable differently as we are. So for my opinion, permanent disable mean I should burn the fuse, which will be not allow this code runs again, never. When the hardware-based root of trust transfer the state of chain of trust to software, that's done because it's no more hardware root of trust exists, it's only software, right? And our system, especially x86 system, it's very complex. It has a lot of boot states. As example, you have a sleep mode, you have a hibernate mode, and it's a different boot states. When you close the lid of your laptop, it doesn't mean your machine switch off. Actually, it saves all the states, and it's why it's recovered very fast when you open the lid again. And only when you make a hard reset and reboot machine, then all the states basically started from scratch. It's why attack surface, it's very complex, and sometimes vendors, they make it secure from the hard reset, but it's hard to know like where it can be failed in recovery, in sleep, or the hibernate, because they want the performance and your system boot fast. It's pretty much it for today, and thank you very much, Ekoparty. So I would be happy to answer the questions. Yes, please. It's fused for the hash for IBB. Yeah, but it's not a fuse for the public private key. Yes, exactly. It's PKCS format. Yeah, yeah.
Have you looked at the parser of that?
Yes.
And nothing found.
So I was used to work for Intel before, and I found a lot of issues there, but it's fixed internally, so
Okay.
I can't speak about that. But I like the way how you're thinking. It's a really right vector. Yeah, actually, the complex parsers inside the firmware, it's really sweet vector because it's no mitigations. Any memory corruptions will lead the code execution, right?
Hey, a question. So you talk about how CPU microcode is not being protected and can be altered.
Yeah,
but my question is the certificate or the private key stored in the TPM altered if I change the microcode in the CPU?
So no, microcode actually doesn't rely on any TPM verification. It has some other verification routine from CPU, but problem is if you have, as example, microcode, you not modify microcode, you just downgrade the microcode with known issues. It's a bit different story. So basically, verification, if the keys or like this microcode version not been blacklisted, you will be still able to boot it. And yeah, so it's kind of open, interesting room, and especially, as we know, it was a lot of speculative execution issues past 2 years found on Intel architecture, and especially microcode downgrade can allow you to use these known issues even if it will be patched on new versions of microcode. And it's kind of like scary, but new, I would say newest generation of Intel CPUs, they have some protection from that. But back to the Skylake, not.
Thanks.
Okay, let's do last question. No questions? Thank you very much, guys. Thank you.